SAIL's mission, its role in the shuttle program, is testing. Testing is a key task in the engineering process of developing a new product or modifying an existing product. The surest approach to testing is to perform tests on the product itself. That works fine for something like an automobile, but not for the space shuttle, which is so complex and so expensive that we only have a few, so we cannot afford the monetary or safety risk of such a test approach. But we can get close to that approach. We can put a space shuttle in a building. At least, we can put those parts of the shuttle that are appropriately housed in a building, parts such as the cockpit and the aviation electronics, otherwise known as the avionics. We add more electronics, especially computers, to simulate the rest of the shuttle. Then we hook up that shuttle to computers that will simulate the environment that our shuttle will fly through: gravity, atmosphere, winds, and so on. Now we have a shuttle that can fly, allowing us to look at all phases of flight: pre-launch, ascent, on orbit, entry, in real time, meaning that operations to be performed on an actual shuttle flight will take the same amount of time when we run in SAIL. Then we bring in equipment from Florida to enable us to test the pre-launch portion of a flight. Finally, we add test equipment to gather data during each test so we can determine whether or not the test was successful. And that gives us the Shuttle Avionics Integration Laboratory, or as we call it, SAIL. Let's take a quick look at the various parts of the lab and how they've changed over the years. At the heart of the lab is the primary test article, the orbiter, which is that part of the shuttle that goes into orbit around the Earth and returns to land like a glider on a runway. SAIL's orbiter consists of a cockpit, payload bay, avionics bays, avionics, and cabling, all built and positioned just as in the orbiters that fly. But we need more than an orbiter, so we have more elements that make up the total lab. The Marshall Mated Element System, or MMES as we call it, is a mix of flight and lab equipment to simulate the propulsion elements, that is, the main engines, the external tank, and the solid rocket boosters. The Shuttle Dynamics Simulator, or SDS, generates real-time 6 degrees of freedom simulations required to represent the vehicle environment. The Payload Avionics Test Station, or PATS, is used to simulate the operation of selected payloads in the shuttle. The Launch Processing System, or LPS, is a subset of the Kennedy Space Center hardware and software that launches the shuttles. The set is installed in SAIL to verify ground checkout and launch control functions. The Global Positioning System Test Station, or GPS, simulates the constellation of GPS satellites visible to the orbiter at any time during SAIL testing. The Shuttle Avionics Test Set, or SATS, loads, controls, and dumps the flight computers. The Test Operations Center, or TOC, contains hardware and software for acquiring, processing, displaying, and recording test data transmitted by the SAIL flight system and other laboratory simulation elements during SAIL testing. The Non-Avionics Test Station, or NTS, provides the simulation of thousands of temperatures, pressures, valve positions, door positions, and other sensors located on the shuttle. Well, those are the parts of the lab. Together, they constitute a space shuttle environment and ground services. Now, let's talk about the test team. The number of people required to run each test varies depending on the type of test, but the average is around 16. Operators are required for each element of the lab that is involved. At least one person is required in the cockpit. That was always an astronaut or representative from the crew office, but as the astronauts are increasingly involved in non-shuttle roles, the commander is usually a sailor who has been certified to fly the test scenario. Technicians help in the cockpit, including configuring all the switches to the proper position for the start of each test. Subsystem engineers monitor their systems from their stations in the Test Operations Center. Quality control personnel monitor the test to make sure procedures and processes are followed. And the entire test team is led by the test conductor. Each test follows a predetermined test script, which is based on flight procedures that have been modified as necessary for the lab and the objectives of each test. Each test team member has their own copy, which is to be followed to the letter for each run. If anything unexpected happens during a test, that is, something other than what's in the test procedure, the event is documented as an anomaly, also known as a nonconformance, or NC, and is assigned to a sailor for troubleshooting and resolution. Often, these nonconformances turn out to be a lab-related problem, but they have also documented problems which led to corrective action for flight hardware, flight software, or crew procedures, even after flying for nearly 30 years, which is, of course, why we run these tests for each and every mission. This work includes incorporating any changes to the avionics that are made to the fleet. SAIL installs and flies these changes first, before any of the other orbiters, so that we can catch any problems with installation or implementation before they impact the fleet. These engineers and techs also keep the equipment operating by performing preventative maintenance and problem troubleshooting and correction, so that when the test team is ready to run a test, the lab is ready for them. Lab configuration also includes preparing initialization points, known in the lab as initial conditions, or ICs, so that each test begins at a predefined, repeatable point in the flight profile, generally during pre-launch, on-orbit, deorbit, or entry. Of course, both the flight system and the environment have to be initialized to the same point. So, when we start a test, our orbiter thinks it's really at liftoff minus 30 minutes, or 5 minutes, or on orbit, wherever the IC point puts the flight system and its environment. Designated personnel have the responsibility of preparing these ICs for each test. So, the lab gets prepared to run a test. Much effort goes into each test, before, during, and after the test, but a successful shuttle flight is well worth it. SAIL has been testing for quite a while, going back to the late 1960s when the concept of an orbiter test bed was born. This is the earliest SAIL in 1973. The cockpit was located in the Building 16 High Bay. Rockwell International was selected by NASA as the prime contractor for the orbiter in 1972. Rockwell personnel came to prepare Building 16 to support the approach and landing test, or ALT phase. For ALT, the orbiter was carried aloft, mounted atop the shuttle carrier aircraft, a 747 jumbo jet. The orbiter, with an astronaut crew on board, separated from the carrier aircraft and maneuvered to a landing on the lake bed at Edwards Air Force Base. SAIL support for these ALT flights began in 1974 with the dismantling of the early SAIL configuration, replacing it with a high-fidelity orbiter built and positioned to replicate OV-101 or Enterprise. Avionics bays were installed. Wire trays were installed along the length of the payload bay. The Test Operations Center was located on the first floor, with stations for members of the test team. SAIL testing contributed to the successful completion of the 5 ALT flights of the Orbiter Enterprise in 1977. The shuttle program then moved into the next major phase of shuttle development, known as the Orbital Flight Test, or OFT. An OFT flight consisted of liftoff from the Kennedy Space Center, several days of on-orbit operations, and deorbit to a landing at Edwards Air Force Base in California. SAIL support for the OFT flights began in 1977. Converting the STS flight system to the OV-95 configuration required extensive modifications. This view from inside the cockpit shows the wiring modifications in work. A tremendous amount of wiring was added to the cable trays in the payload bay, much of which was needed to support the main engines and solid rockets used during ascent. The MMES was added to provide the propulsion elements used during ascent. The LPS area, with its mini firing room setup, was added to support testing of the pre-launch sequence. SAIL completed these modifications and a huge amount of testing, operating the lab 24 hours a day for at least 5, sometimes 6, sometimes 7 days a week in preparation for STS-1, the first shuttle launch, which occurred in April of 1981. Since STS-1, SAIL has tested for every shuttle mission and has installed modifications to stay current with the shuttle fleet and to upgrade its lab equipment. Some of these mods were major, taking over a month to complete. As the years passed, changes were made to the flight system. The MMES, the SATS, the SATS, or the SDS, the Shuttle Dynamic Simulation, and the Test Operations Center, TOC. As the shuttle program nears its projected completion in 2011, the modifications have slowed to a trickle, but the testing continues, as the program continues to do all it can to verify that the space shuttle is as ready as it can be for each and every flight. Despite its complexity, SAIL has always done its job. Testing requirements for every mission have always been completed in time for analysis, usually ahead of schedule. The lab has been recognized for its achievements throughout its history. For example, NASA presented this award to SAIL for work performed in support of the first orbital flight, STS-1, in 1981. Many shuttle crews have shown their appreciation for the work done in SAIL. For example, this plaque was presented to SAIL by the crew of STS-40 in 1991. SAIL testing is a major factor behind the fact that there has never been a major in-flight problem with the avionics of the space shuttle, going all the way back to STS-1 in 1981.